Okay, so the issue is library car and library lawman both have objects called salaries in them. And so if you load lawman first and then car, the salaries object in car is going to overwrite, or not overwrite, but mask the salaries object in lawman. So if you want to use the salaries object in lawman, load library car first, and then load library lawman. Okay, and then it will say the following object is masked from package car salaries. Okay, but if whatever reason the thing you want is masked by another thing, you can always reference it using the double colon notation. And so if I want to get the salaries object in car, I do car double colon salaries. Okay, and this will pull up the salaries object in car, which we can see here. This is like the professor salaries. Whereas if I just type in regular old salaries, we get the baseball one. Okay, or you can always reference it directly, lawman : salaries as well, and that's the exact same thing. So 2 colons, package name, 2 colons, and the object name will always reference that particular object in that particular package. So that's one way to deal with it. Okay, any other general topics or issues? Feeling okay, I hope? Okay, so today we're going to continue on in our discussion of multiple linear regression and talk about data transformations. I know some of you were asking questions about this in Piazza or sending me emails regarding the midterm, and I know I did not cover this explicitly. So I'm not going to like penalize anybody for not doing any of this. But if you wanted to do it as part of your analysis, always open to you. Okay, so here is if we're going to transform just the y variable, one way we can think of it is we can think of the y as equaling a function of a multiple linear regression model. Okay, so we have the regular multiple linear regression model as it appears here, but then there's a function g, and so we can model the inverse of g of y as standard multiple linear regression. And so to kind of explore this, we can do an example, and we're going to try modeling the rates of defective products at some factory. Okay, and so so this is coming from our textbook, and what we're looking at is there's a factory production process, and a bunch of their parts are defective, and they're saying there's one guy says the reason why it's bad is because the temperature is no good. Okay, and we have to do something else, and someone else says if we get a handle on the density, the defective rates will go away, or if we just reduce the rate of production, that will fix our problems. And so so we want to just kind of explore what all of this could mean. So here we're plotting the defective rate versus the temperature, and we see this, and it looks linear, or there could also be some kind of curvature here. It's kind of difficult to say. It looks like there might be some curvature, because if it were truly linear, we'd probably expect these 2 lower points to be somewhere down here. Versus density, again, it's a little hard to tell. Okay, it could be linear. Maybe there's some curvature. Okay, so somebody could say it looks like it's doing that, or someone else could say it's going straight. Same story here. So it's a lot of this is some judgment calls on whether there's some curvature there, or if it's a straight line. Okay, so we try fitting a model. Oops. In here, I'm just modeling the defective as a function of temperature, density, and rate. earlier on in the code, and I'll post the RMD for this, I did attach the data. So I attached the data so I can reference them just by name. Okay, and so what we see actually none of our things are coming out significant in terms of its impact on the defective rate. But let's take a look at our standardized residuals. Okay, and here I think we're starting to see kind of maybe a little bit of this V-shape-ish taking effect here. And again, it's not super clear, but it does seem like overall there is some kind of V-shape. You know, we've got a lot of empty over here and empty over here, and kind of emptiness up top here. So there might be a little bit of a pattern here, and so it might be worth exploring transforming our data. Okay, so again, you know, emptiness in these corners. This is kind of common across all three of our standardized residual plots, looking at the different x variables. Okay, and then so finally we plot the standardized residuals versus the fitted values themselves, and we also see the same phenomenon of, you know, kind of empty corners, indicating, you know, there might be some kind of V or U type shape going on here. So, so one thing we can do is apply an inverse response plot. Okay, and so this is coming from library car, which some of you guys are familiar with already or have used. I know we've covered it before. And so we use the inverse response plot, and we're, you know, try fitting a few different lambda options, and it seems that the one that it tells us to use is 0.44. And so we could use lambda equal to 0.44, but maybe for the sake of interpretability, even though interpreting any type of transformed variable is challenging, we can apply a square root transform, which is effectively lambda is equal to 0.5. Okay, so it's a value close to the estimated lambda. So, so we're going to use lambda equal to 0.5, taking the square root of y. And so, well, I guess maybe I should have kept the code in our thing. And so here I'm plotting temperature versus, whoops, the square root of the defective rate. So all I've done is just take the square root of the defective rate, oops, and if we do that, it does seem to kind of straighten it out. So if we look at the temperature versus defective rate, so this is square root of the defective rate versus temperature of the defective rate non-transformed. Okay, so comparing this versus this, it seems this has straightened things out. Okay, and the same can be said about square root of the defective rate versus density, and square root of the defective rate versus rate. Okay, so these things, by applying a square root transformation, it does seem to help us in terms of straightening out the relationship between rate and each of these things. And so the question now is, okay, well, can we fit a good model? And so we try explaining the square root of defective as explained by temperature, density, and rate. And our model ends up looking like this. And so what we see is that temperature and density appear to be significant, at least at the 5% level, whereas rate is not significant. And we can look into this a little bit more closely. So this is our transformed model. Okay, so looking at just kind of to see if this even works in the first place, we'll plot the standardized residuals versus our temperature, and this seems to be a bit better. I mean, we do have kind of pockets here and here, but in terms of overall the spread, it's I think this is mostly just because we lack a whole lot of data in this section. There doesn't seem to be really a U or any kind of shape here. And it's not like the pockets are uniform across the different standardized residual plots. So here again, I'd be hard pressed to say there's any kind of pattern in these residuals or these ones as well. So overall, it seems like the patterns that we saw in our standardized residuals before seem to be doing better here. Okay, and so if we plot the square root of y versus the actual fitted values, so this is kind of an overall measure of how well our fitted values do to predict the thing. In this case, we're trying to predict square root of y. It seems like it does a fairly good job. Okay, but that's the full model, including the non-significant rate variable. So we can try looking at the added value plots of each of these things. And it does seem to indicate that looking at rate, the rate variable does not seem to have a major impact in terms of added value. So because of this, we'll try removing the rate variable from our analysis. Okay, so I'm going to do square root defective as a function of just temperature and density, and that makes these are both still significant. Now this is about 1% significant, which is good. Okay, and you know what, we're losing the rest of the details. Let me just get our data entry here. So if we compare the details, this is our transformed model, including rate. We can see the adjusted R squared value is 0.9365, and if we remove the rate, we see the adjusted R squared value is hardly affected, 0.9352. So the removing of an extra variable here doesn't reduce our ability, or our model's ability to explain the variance in y. So that's a good thing. Okay, we should always try to go for the simplest model that captures the variation that we want to explain. As far as making interpretations from our estimates, this is it's a little bit harder to explain now that we're dealing with the square root of the defective rate, but it seems that temperature and density do impact the rate of our defective products here. Okay. And so this is the fitted values versus the defective when we've removed rate, and it looks almost exactly the same as when we included the rate. So removing rate probably has minimal impact on our model fit. So that's good. Okay, so in this case, these things aren't fitting as I thought they were. We can try, so that was an example where we just transformed the y variable. Okay, maybe we need to transform x variables as well. Okay, so both the response and the predictor.
A quick question.
Yes.
So you know how you had the plots for the residuals for each of the predictors?
Yes.
What's the difference between doing that and just using the plot function for when you run your model?
So the plot function, let me just make sure I can explain what each of these ones are doing. So let's do plot. We'll do the untransformed one. Okay. So here it's just plotting the residuals versus our fitted values. Okay. So the fitted values is kind of like an overall. If we include all of these variables together, how does it, what is its prediction? It's the fitted value. So that kind of combines all of the x variables into a single value via the y hat, essentially. By looking at them individually, you can kind of pick out to see if one of your predictors is behaving poorly. Okay. That said, just because one of the predictors is behaving poorly, the answer may or may not be to transform the misbehaving predictor. It's just because a lot of times the predictors are correlated. Transforming one but not the other might result in unexpected results, and so it's hard. Okay.
Question?
Yes.
So when you're looking at the residuals versus fitted value plot,
Okay.
I know that we generally don't want to see a pattern, right?
Yes, no pattern.
What usually is the way to look at this plot? Like, what can I tell from this thing?
Okay, well, so it tries to fit this, this red low S line. And so here we see like a little bit of a U. And so that says, maybe there's a pattern here. Okay. So, ideally you want the red line to be flat, and you want the amount of spread and the residuals also to be flat. So let's, your scale location, this is kind of, does the amount of spread in our residuals remain constant? We want the red line here also to be flat. So in our perfect model, all of these red lines that we see in the middle of our data would be very flat. Of course, never will it be perfectly flat unless you have artificial data, but ideally you want something as close to flat as possible for all of your kind of diagnostic plots here. Yes?
Scale location lines are flat, but it's not in the middle of the graph.
It
Flat, but it's maybe it's an upper area.
that should be fine.
Because I came across this kind of picture.
I'm imagining you just have like a few standardized residuals that are incredibly small, whereas most of your data residuals are up here or something. I don't know. I'd have to look, but flat is always good. So
They don't have to be really in the middle.
it doesn't have to be perfectly in the middle, because if you look at square root of the standardized residuals, the graph starts at 0 and goes up to something else. Okay. Around 1.5 to 2, something like that. But yeah, it's not always. I don't know what the middle per se would be. Okay. Yeah. Another question.
So, say if we have like a list of predictors that are all significant, so what you're saying is it would still make sense to try to reduce make it into as few predictors as possible and still have a good fit to the data, right?
Well, if all of your predictors are significant, then you should probably keep them.
Keep all of them?
If they're all significant, yeah. you know, if you have multiple predictors that are very correlated with one another, then chances are you'll find that not all of the predictors are significant. One of them will do a better job explaining the variation in y than something else that's highly correlated with it. But you know, if you have multiple predictors and they're all significant, then I don't see a reason to throw any of these predictors away. Okay, and unless you have a reason based on your knowledge of the subject that says, well, you know, this particular thing isn't interesting, so or something, but generally you probably want to keep them in there, at least to account for the effect of that predictor in the result. Yeah. Another question?
If one variable is significant, but it only increased the R squared a little bit, do you keep it or?
Yeah, that's a hard question. If it's significant, but it's only increasing R squared values by a tiny bit, do we keep it? I guess other people might disagree. I would probably say yes. The R squared is not the end all be all of everything. It's just kind of like an overall, like a value on what it's doing. I guess comparatively it would be like saying how much money someone makes is a measure of how important this person is to society or something, you know. It's not the best tool. It is true to some regard that people who make lots of money, maybe important is not the right word, but maybe have more responsibility or have more whatever overall, okay, but to use that as the only criteria would not be wise either. Okay. All right. Okay, so that was an example where we just transformed the y. Now we can talk about transforming both the x variables and the y variables, and my graphs here are getting their x-axis cut off. Okay, so here we are looking at some magazine data. So I know we looked at magazine data earlier in the class, but here we're looking at magazine data again. We have 3 x variables and 1 y variable. Our y variable is the ad revenue for the magazine. So how much money does the magazine generate from advertisements, which is probably the magazine's primary source of income. But then we're also looking at a few predictor variables. We've got ad pages, which is how many pages of advertising there is, okay? How many pages there are. We're looking at subscription revenue, which is how much money the magazine makes from subscriptions. So here's a magazine that makes a lot of money from subscriptions, but the amount of income it makes from advertising is, you know, kind of over here, things like that. And then we're looking at the last one is how much revenue the magazine makes from sales at newsstands. Okay, so you think of where can you get magazines? You can purchase a subscription, or you can purchase it at the newsstand. I guess today you can purchase on your iPad, and I'm not sure how those would be counted in this model, but probably I'm thinking like one-off purchases. If you're just buying a single issue, there would be a newsstand, whereas if they're mailing you the issue, it would be a subscription. All right, so there's a few ways to handle this. We can transform the x variables separately from the y variables, okay? And the code to use, you need to use library car, and you just take your data set. In our case, our data set is magazines, so I can do kind of head of magazines, and we can see the columns available in magazines is the name of the magazine, its ad revenue, how many pages of advertising it has, its subscription revenue, and newsstand revenue. Okay, so obviously we can't transform the magazine column, so we have to remove that. And if we're going to transform the x variables separately from the y variables, we're going to get rid of the ad revenue column as well. All right, so in this case, I'm subsetting magazines so that we are removing the first two columns, and that's using just bracket notation, saying all the rows, but which columns? Just not the first two. Okay, so this would be the data. So this is just our x, and I just feed this into this function called power transform. Okay, and power transform in of itself will do all the math, but what it spits out just is kind of its predicted power transforms, and so often it's more helpful to us if we use the summary function in conjunction with power transform. Okay, and so this is, it just spits out a whole bunch of information, and it says kind of like, we're thinking you should use these numbers here, okay? And so if we look at these things, the estimated power in comparison to the standard error, these are pretty much not significantly different from 0, with the exception of newsstand revenue. This one is slightly significantly different from 0. It's more than 2 standard errors away from 0. However, it might not be the worst idea to just do a 0 level power transform, because 0 level power transform would be taking the log of all of our numbers here. Now, some of you guys might have encountered this problem as you were doing your midterm exam. If you try to apply a power transformation and you have negative numbers or 0, okay, you're going to run into problems, okay? Because if you take the log of 0, you get negative infinity, right? So, so what do we do in these cases? And this is, there's a whole bunch of things you can do, and none is right or wrong, okay? And it's just kind of, so one option is you throw away all of your zeros, okay? And you say, well, these I'm going to exclude from my analysis. Another option is to just add a constant. And that constant can be any value. It can be 1/2, it could be 1, it could be 10, it could be whatever. You just add a constant to all of your values, do your power transform, take the log of all those things, and then do your analysis that way. And adding or subtracting a constant is fine. Power transformations, if work best if you have values that are at least one magnitude larger than another. So if you're going to do like a log transform, you don't want, if all of your values are like from 1 million to 2 million in value, okay? You don't have, it's a spread of 1 million, but when you take the log, the log of 1 million versus the log of 2 million, it's not incredibly, there's not a huge difference here, okay? Whereas, obviously, if I subtracted 800,000 from 1 million, okay, so if I do minus 800,000, that's 80,000, okay, 800,000, and I do 2 million minus 800,000, Oh, well, in this case it's well, maybe I should subtract off more, like 950,000. But if you get these things kind of in whoops, what am I doing here? It might make sense to just subtract a constant if you've got things kind of not within an order of magnitude of each other, to kind of artificially create more spread in your transformed data. So you can subtract values, or you can add values to y before you try to apply a power transform. And any of those are acceptable. In terms of like picking a constant to use, there's not a whole lot of guidelines that said this is good and this is bad. It's just kind of like, well, whatever works to get it in the range that you want. So anyway, if you have all strictly positive, no zero values, you can do summary power transform, and this works here. Okay. And so in this case, one option would be to apply the 0, 0, 0 transform to the columns ad pages, sub revenue, and news revenue. Okay, and so we would fit a model. Okay, and so we would do model is lm of ad revenue as explained by log of ad pages and log of subscription revenue and log of news revenue. Okay, and then we can look at the summary of our model. Okay, and so everything is significant here, but then what we want to do is we then want to apply do an inverse response plot to see if y ought to be transformed.
Question?
Yes.
So the reason why you did log transform is because all the coefficients or the powers are close to 0.
Yeah, so when I did power transform, the estimated powers to use were 0, or very close to 0, or at least, compared to the standard error, is close to 0. So this kind of gives you a sense of like what acceptable power transforms would be. So 111 means leave it untransformed.
Right.
000 means do log on all three. And this would be 00.08, which would be log on the first two and then transform the third one by a power of 0.08, which I don't really know what that would accomplish or what that does, but then that produces the highest p-value in terms of this would be the least troublesome, okay? So anyway, I'm fitting the log of the x's to add revenue, and then we're going to so here I can do summary model, and I can even plot the model and just kind of see what this looks like. So this is our residuals of our fitted values, and so we see some problems here clearly still exist. Okay, so we're going to try transforming our y, and so I do an inverse response plot of the current model where the x's are transformed but the y is not transformed. Okay, and so when we do this, we look and we see, okay, perhaps we should transform y. Okay, and so this says use lambda equal to 0.23. But if we're looking at this thing, okay, the lambda equal to 0 doesn't seem all that far off either. Okay, so we can do lambda equal to 0.23 as which is this black line here, but because the green line and the black line are pretty similar, and in terms of the fit of the data, the green one doesn't seem so terrible, we can just do a log transform to y as well. Keep things easier, just log everything. We don't have to, there's no requirement for that, okay? So I can just create model 2, and now I'm going to fit log of everything. Just now we're going to do log of ad revenue. I could do ad revenue raised to the 0.23 power. Okay, so we do this. We can ask for summary of model 2, and now everything's significant except for news revenue is significant at the 10% level, newsstand revenue. Let's take a look at our diagnostics plots. Again, we're not looking at individual ones here. We probably could, but we look at the residuals versus the fitted values. This looks a lot better, right? Okay. And we try this. Okay, so we see maybe some potential problems with our standardized residual things, but this looks pretty good. We're seeing kind of just this nice ball of residuals, and this looks pretty flat. There's still a little bit of a kind of a tiny bit of a curvature, and that's probably because we used the 0 instead of the 0.23, and everything here is nice and flat. So that's good. Okay. So that's one way to do it, transforming the x variables separately from the y. The other option is to do them all at the same time. A lot of times you'll come to the same conclusion. Sometimes you come to different conclusions if you do the x first and then the y versus the x and y at the same time. Why is that? Well, I guess yeah, I'm not sure how the algorithm behind calculating the power transforms works, but it does behave a little bit differently. And so, which one should you do? Well, you can try one and see if it works, and then if it seems like it works, then keep it. Okay, if it's not broken, don't fix it. On the other hand, if one didn't give you quite the results you were looking for, you can just try transforming them all at the same time. And so in this case, I'm just removing the titles column, and I'm doing the same type of thing. I'm doing power transform of our basically our data frame without the titles column. If your entire data frame is numeric, you can just do power transform data frame. You don't have to remove any columns. But because I have a character column, power transform says, I'm stuck. So we do that, and then we look here, and looking at this, okay, we see again our numbers are pretty close to 0. The two middle ones, their estimated power is within one standard error. Okay, so these ones, it zeroes out. The ad revenue has a non-zero standard error. Its estimated power is more than one standard error away, or more than 2 standard errors away. And the news revenue is also a little bit more than 2 standard errors away. So we have a choice, okay? We can try applying the 0, 0, 0 transform, which is just taking the log of everything, which is what we did before. And here it says the p-value associated with that is, less than 1%. So that may or may not be the best one. The other option is to do this funky, 0.11, 0, 0, and 0.08. What's going to give us the best results? In terms of the data that we have, this one will probably give us kind of the best behaved results. Is it wrong to choose one over the other? Not necessarily, okay? the transformations, as you do weirder ones, the interpretation, ability to interpret becomes more challenging, and you might not be able to give a good explanation of how these variables relate to one another anymore. But on the other hand, if you're just using your regression model to make predictions based on the data you have, this one will probably give you nicely behaved predictions. So in this case, we can create a final model here where we're raising ad revenue to just this weird power of 0.11, and we're going to do news revenue raised to the 0.08. Okay, because we've already seen the relationship of taking the log of everything. So I'm going to call this one model 3, and we'll invalid power and formula. Did I do something here? Maybe I have to create a will be ad revenue. I might have to do the transformation out here separately. Sorry. TY and TX3. Okay. So we're going to do this, and we do that. And we ask for summary of model 3. That looks pretty good. I mean, it's hard to tell, but everything's coming out significant, which is nice. And then we can do plot model 3 and just take a look at the residuals versus fitted. So this looks nice. You know, a little bit of stuff going on down here and here, but that happens. This looks fairly good. Tiny bit of curvature, but overall pretty nice and flat. And that looks good too. And we can do kind of a fitted values, model 3 $. Is it? Yeah, I forget what the. Fitted dot values. Okay. So we'll plot transformed y, fitted values versus our transformed y, and that looks pretty good in terms of straight line regression. So yeah, and as far as transforming data goes, we have some nice tools that exist in R. This power transform, you just throw in a data frame, and it will try to figure out the appropriate power transformation. It's just when you make interpretations, if you use some weird coefficients for your power transformation, the understanding of how one variable affects to another just gets a little bit more muddled. Okay? All right, so that covers that section. So we'll see you guys. Oh, Wednesday we have off, right? Because it's Veterans Day, so we'll see you guys on Friday. So enjoy your day off, and thank anybody you know who served.